Hello all, and thank you so much for tuning into this talk. In this presentation, I'll be discussing some research I've been doing these past few months, which is characterizing the latitudinal diversity gradient of late Neogene Planktic Foraminifera in the Tasman Sea. This talk is an update on the project with our preliminary conclusions that will be followed with some future directions for this research. The history of global Planktic Foraminiferal diversity patterns is well known. Within the Neogene period, a stepwise increase in diversity occurs, which I've pointed out here with the red box and arrows. However, several questions remain regarding Planktic Foraminiferal diversity, such as what drives this stepwise increase in diversity through the Neogene? What regions produce local diversity that then scales up to global diversity? To begin to tackle these questions, we can investigate basin scale latitudinal diversity gradients. But first, a quick reminder of what the latitudinal diversity gradient is. The LDG is the observation that diversity of organisms is highest in the equatorial regions and declines quickly towards the poles. This observation was first made in the early 1800s and has since received much attention from biologists and paleobiologists. The figures on this slide are from a study by Economo and others, where they found that the LDG for ants is quite strong. Diversity drops significantly at latitudes higher than about 20 degrees north and south for this ant group. However, the LDG doesn't hold for all organisms today. For example, some European bryophytes and carnivorous diving beetles obtain their highest diversity between 40 to 50 degrees north latitude. Patterns of peak diversity at higher latitudes have also been found for the Planktic Foraminifera. Studies of the modern Planktic Foraminiferal LDG using core top data indicate that diversity for this group peaks around 20 degrees north and south and is mainly influenced by temperature. Other studies have quantified the Planktic Forum LDG through geologic time. One study by Yasuhara and others found that for 4 time slices since the Pliocene, the LDG shifted in response to surface water mass movements across cooling and warming intervals. They too found that peak diversity occurred away from the tropics, and in the Pliocene, their data indicated peak diversity around 35 to 40 degrees north. Earlier this year, my colleague and I published a paper where I calculated diversity curves at 3 sites across a Kuroshio Current extension, the major subtropical western boundary current in the Northwest Pacific. We found diversity of Foraminifera was highest on the northern edge of the current back to 12 million years ago. Diversity changed in response to major tectonic and climate events. For example, during the final stages of Central American seaway closure, diversity slowly became highest at our northern site. We interpret this pattern to indicate a proto-Kuroshio Current extension was prevalent in the Northwest Pacific since the Middle Miocene. Our study also contradicts modern LDG studies, which indicate a diversity peak around 20 degrees, whereas we found peak diversity to occur as high as 37 degrees north latitude, a finding that more closely agrees with the Yasuhara and other study from the North Atlantic. After our publication on diversity across the Kuroshio Current extension, I was left with several questions. Namely, is the pattern of peak diversity around 37 degrees instead of 20 degrees prevalent in other ocean basins? And if yes, is this pattern true for other western boundary currents and their extensions specifically? To answer these questions, we investigated the Planktic Foraminiferal latitudinal diversity gradient across the Tasman Sea of the Southwest Pacific Ocean. Here, we used sites that cross the Tasman Front, which is now referred to as the East Australia Current Eastern Extension. For this study, we used the Planktic Foraminiferal biostratigraphies of Jenkins and Srinivasan from Ocean Drilling Program Leg 90 sites. These sites span from the equator to 40 degrees south, thus ideal for comparing patterns of diversity from this area to the Northwest Pacific. The taxonomy was updated to that of Wade and others from the Oligocene Atlas, and the taxonomy of Lamb and Leckie for Northwest Pacific Neogene Foraminifera. The age models for the 7 sites was constructed based on magnetostratigraphy and calcareous nanofossil biostratigraphy, with ages and datums updated to the geologic timescale 2012. To calculate diversity, we first had to calculate the first and last occurrences of each species at each site. From these calculations, we have tables of each species' top or extirpation event and bottom or local origination event for each site, including age errors. From the origination and extirpation dates, we then calculated diversity curves for each site, as well as evolutionary rates using the equations from Foote's 2000 paper. These calculations take into account species that range through the interval, cross just one interval boundary, and those species confined to an interval. Diversity was binned at 100,000 year intervals, whereas the evolutionary rates were binned at 500,000 year intervals. As indicated by Jenkins and Srinivasan in their 1986 paper, most of the Leg 90 sites contain a hiatus in the late Miocene. Most records do at least cover the Messinian into the Holocene. And this is great because we are able to capture 4 important events within these records. The first is the constriction and closure of the Central American Seaway, which occurred in the Pliocene around 4 million years ago. That tectonic event was followed by the global warming event known as the Mid-Pliocene warm period. The intensification of Northern Hemisphere glaciation occurred right after the Mid-Pliocene, in which temperature gradients became more modern-like. Lastly, the Mid-Pleistocene transition is the time in which glacial cycles transitions from 40,000 to 100,000 year cycles. So we can investigate the plankton latitudinal diversity gradient response through the late Neogene across such tectonic and climate events. Of the evolutionary rates, first we'll take a quick look at extirpation rates at each site. In this slide, a modern-day sea surface temperature map with site locations is at the bottom, with geologic time along the left side. There are several spikes within the data, but I just want to point out this one cluster of increased rates that occurs within the Pliocene of the mid-latitude regions. In this slide, we've now overlaid the timing of these extirpation rate increases in the mid-latitude sites with major climate and tectonic events. It seems like the constriction and closure of the Central American Seaway and potentially the Mid-Pliocene warm period in Northern Hemisphere glaciation have a part to play in these rate increases. However, these data are at present quite coarse, so it is hard to hypothesize the event or events that may be driving these patterns. Origination rates are now represented on the right side of each chart for each site in shades of purple. There appears to be 2 intervals in the mid-latitude sites that include increased local origination rates, the first straddling the late Miocene and early Pliocene, and the second within the middle Pliocene. The first mid-latitude origination rate increase that occurs close or at the mid-Miocene-Pliocene boundary could be related to increased constriction of the Central American Seaway. A global increase in origination rates at this time is also recorded from previous studies, such as Way and Kennett in their 1986 publication, and Frass and others in their 2015 study. The second pulse of origination rate increase most closely corresponds with the closure of the Central American Seaway. But like the extinction rates, origination rates are conducted at a coarse resolution, making interpretations about drivers a bit difficult. Here we've plotted planktic foraminiferal diversity at each site. I've also included the tropical site 806 for comparison to site 586. It's important to note that these 2 sites lie incredibly close to one another and should have the same patterns of diversity. However, site 586 exhibits lower diversity throughout the section. This is likely due to site 586 being part of a larger study using mainly core catcher samples, whereas the biostratigraphy for site 806, conducted by Chason and Leckie, was done in greater detail. Diversity patterns are generally as expected, with higher diversity in the tropical to mid-latitude regions, with diversity quickly diminishing towards higher latitudes. This is especially apparent at sites 592 and 593. As I step through discussing diversity patterns across the Tasman, I'll also show the diversity curves from the Northwest Pacific to compare patterns from both hemispheres in the Pacific Ocean. It's not really feasible from these curves alone to look at how diversity, and specifically the LDG, has changed through time, so we're going to put these data in a more readable format. To better quantify the regional latitudinal diversity gradients, we've subtracted the diversity of the mid-latitude sites from the tropical sites. For the Northwest Pacific sites, we use tropical site 806. For the Southwest Pacific sites, we subtracted those mid-latitude sites' diversity curves from tropical site 586. The resulting curve has a positive and negative scale. Negative numbers indicate higher diversity at the mid-latitude sites, whereas positive values indicate higher diversity at the tropical sites. We'll only investigate the patterns of diversity in changing LDG through the last 7 million years, as that's the age of the oldest sediments above a major hiatus at the tropical Southwest Pacific site 586. These are the differences in diversity curves plotted for the Northwest and Southwest Pacific. The most apparent pattern in the Southwest Pacific is how quickly diversity declines south of site 591, which is located at 31 degrees south. Site 592 and 593 both indicate low diversity compared to the tropics throughout the section. Thus, these data indicate that between 31 and 36 degrees south, there's a huge decrease in diversity. This is very different compared to the Northwest Pacific, where the highest diversity was found at 37 degrees north. The second major pattern in the Southwest Pacific is the prevalence of a latitudinal diversity gradient peak at the mid-latitude sites, specifically sites 588, 590, and 591, outlined here in red, from the late Miocene to the middle Pliocene. Intermittent and smaller diversity increases occur at subtropical site 587, from the late Tortonian to the late Zanclean. We layer the tectonic and major climate events over the diversity gradients. It appears that the constriction and closure of the Central American Seaway is responsible for the peak diversity in the mid-latitudes of the Southwest Pacific during the late Miocene to Pliocene. We also found this to be the case for the Northwest Pacific sites. Planktic foraminiferal diversity increased and peaked in the mid-latitude region at the northern edge of the Kuroshio Current extension with tectonic gateway closure. After the Central American Seaway is closed, the Southwest Pacific mid-latitude diversity peak dissipates, with highest diversity shifting back to lower latitudes. This occurs with the establishment of Northern Hemisphere ice growth and may be sustained across the mid-Pleistocene transition. Future directions for this project include combining the diversity data with published geochemical data from the Tasman Sea to further link abiotic drivers of the late Neogene Planktic foraminiferal latitudinal diversity gradient. The figure on this slide is a bit of a sneak preview. Here I have plotted 4 stable isotopic curves from the Tasman, and it appears that when temperatures in the mid-latitudes warm, this is when diversity is highest in these regions. When surface temperatures begin to cool again in the Tasman, this is when the planktic forum diversity peak moves back towards the equatorial regions. There is also limited information about modern planktic foraminiferal species distributions in the Tasman Sea and the modern LDG. So we will use the Census database to map species abundances and calculate the modern latitudinal diversity gradient. Thus far, our major findings from the study indicate that the planktic foraminiferal latitudinal diversity gradient in the Northwest Pacific is very different from that of the Southwest Pacific. Specifically, there is a strong and stable LDG peak in the mid-latitudes of the Northwest Pacific, whereas the LDG mid-latitude peak in the Southwest Pacific is confined to the late Miocene to middle Pliocene. From preliminary geochemical data, it appears diversity trends in the Southwest Pacific are controlled by expanding and contracting sea surface temperature gradients. Thank you all so much for attending this talk. I'm very happy to take any questions you all may have at this time.